Okay, so now we're into kind of some of the more fun examples where these are, kind of pushing the limit of what you guys would be doing. And I just want to give you a couple worked out examples that I talk through while we go through them. So the first one I'm going to do is beam 01. I'm running out of good engineering paper. I probably need to go get some. I do most of my calculations in Excel now, so I can keep track of them and update them and change them pretty easily. So I don't often work in paper anymore. So the first one was beam 1, where they gave us a beam, our left reaction, and our right reaction. We want to know what it takes for this system to be in equilibrium. We know that there are 10 spaces at 2 meters each. And they've given us, we need to know what that needs to be, and they've given us a series of forces. Am I going to draw enough of these? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and each of these is 2 meters apart. We know that we can sum our forces in the x direction, with that's positive, and we want to know what it takes for this to be in equilibrium. The only thing we have is our x reaction. So we know that for this to be in equilibrium, our x needs to be 0. We can also sum our forces in the y direction, where upwards is positive. And we want to know what it takes for this system to be in equilibrium. Well, we've got all of these forces acting downwards, which is negative, and these two forces acting upwards, which is positive. So we've got -4, -5, -6, 7, 8, 9, 10, 11, 12, 13, 14, plus our left plus our right, all equals 0. Well, we have two unknowns. Two unknowns is not that helpful. Let's clean this up and make it a little bit better. We know we have our left plus our right. If we add all of these up, it's -99. Let's bring it over to the other side here. We've got 99 kilonewtons. And this is where I ask myself, when I solve this, I don't have enough to solve this yet, what side do I think is going to be higher? Are my left reaction or my right reaction going to be higher? And it looks like I've got most of my load over here. And this is what's really helpful. Right now, stop and write yourself a little answer here that you think your reaction on the left side is going to be less than your reaction on the right side. Because look, most of the load is over here. And you know intuitively that that's going to keep most of the load over on this side. But we can't solve this yet. Let's sum the moments about a point, saying everything in that direction is positive. I am hella lazy. I almost always pick the left-hand side to sum my moments about. You don't have to. I just find it's consistent. I always know where I stand in my calculations, and so it makes my life a little bit easier. It becomes methodical. It becomes repetition. It becomes really easy to know if I lose track where I stand. So I am going to spin this about my left-hand reaction. And I want to know what it takes for this to be 0. Well, to be a moment, you need a force and an eccentricity. Our 4 kilonewtons passes right through. That means its eccentricity is 0. So it doesn't cause a moment. Our left reaction passes right through it. We're spinning it about that point. We're putting a thumbtack right there and trying to say, how does this paper move? Well, that's not going to make it move at all. It's not going to make it spin at all. It tries to make it go up and down, but it doesn't try to make it spin, nor does Rx. So all three of these forces, now Rx happens to be 0, but all three of those don't try to make it spin. Our 5 kilonewtons, if we put a thumbtack right there, 5 kilonewtons tries to spin the paper like that. Or I could say that if I took my hand and curled my fingers the way it's trying to make it spin, this is my right hand, my thumb points down into the page. That way for a moment is negative and that way is positive if we use our right hand rule. And it looks like all of these do the same thing. So all of these try to spin it in the negative direction. And each one of these distances is 2 meters. So we have -5 times 2, -6 times 4, -7 times 6, -8 times 8, -9 times 10, -10 times 12, -11 times 14, -12 times 16, -13 times 18, -14 times 20, but we're still not done. We have this Rx that if we put our thumbtack right here and tried to spin the paper in the direction it pushes, and you can actually do this, it tries to spin it in that direction, which is our positive direction. So plus RR times 20. And all of that needs to equal 0. Well, we can rearrange all of this, add all of those multipliers up, and then divide it by 20. We get RR equals 60.5 kilonewtons. So we can solve this big long equation, which is just about plugging it in very carefully into your calculator, and you'll get 6, and then dividing by 20, and you'll get 60.5. Well, now it looks like we have another known here. We can go back and solve this equation. RL is going to equal 99 minus 60.5, because we're going to bring this over to the other side. And RL now equals 38.5 kilonewtons. So for this beam to be in equilibrium, our right reaction needs to be 60.5, and our left reaction needs to be 38.5. So let's do the diving board question. We have this free body diagram. We have somebody standing on the edge of the diving board, and they weigh 1.5 kilonewtons. Rx, RL, RR, and we've been told that this is 1.2 meters and this is 0.4 meters. And we want to know what RL and RR need to be for this system to be in equilibrium. So let's start with the sum of the forces in the x direction, where that's positive. Well, we have Rx equals 0. I'm going to jump right to the moment. You can do these in whatever order you want, but I'm going to jump to the moment one now. So we're going to spin this about, I'm going to pick the point RL. Again, because I'm lazy. I like to pick this point right here. We're going to spin it about this point right here. And we want to know what it takes for this to be in equilibrium. Well, Rx passes right through the point and RL passes right through the point. So they don't contribute to the moment of trying to spin it about right here. RR does try to spin it about this point. You can see that if we tried to, it would spin it in that direction. So plus RR times 1.2, because it's our force times our eccentricity. Our 1.5 kilonewtons, pushing down like this, would be trying to spin this in that direction, or our negative direction. So minus 1.5 times, and its eccentricity is this, or 1.2 plus 0.4. And we want this to not move. We want to know what it takes for this to be in equilibrium, or for this equation to be set to 0. We can rearrange this, and we can get that RR equals 2.0 kilonewtons. Now, let's go back and sum our forces in our y direction. If upwards is positive, we know that we have RR. Well, this answer was positive. We drew our arrow positive. That means we were right. We guessed right. We don't know what direction these unknowns are. We have to take a guess. I usually guess that they act upwards. If I get a negative answer, that means I was wrong, or that the force goes in the different direction from my arrow. So let's take a look here. We're going to sum the forces in the y direction and see what it takes to be in equilibrium. Well, we've got RL acting upwards or positive. Again, I'm not sure really in the world what direction that goes. I'm guessing that it's positive. I guessed that RR was positive, and I got a positive number, which meant that my guess was correct. And then we have our applied load of 1.5 kilonewtons. And we want to know what it takes for this to be in equilibrium. So if we rearrange this, we get RL equals minus 0.5 kilonewtons. That negative number means that my guess was wrong. This real free body diagram looks like this. Now you can imagine, we should always draw our dimensions as well. You can imagine that if you have a teeter-totter and a support here, or if you have a diving board and somebody stands on the end, the back wants to kick up. We're holding down on the back rather than pushing up like we would on most things. So it makes sense that this arrow would be in the opposite direction. We're trying to hold it down. Our reaction is trying to pull the back end of that diving board back down to the ground. Let's do the same problem, but change that distance. We've got 1.5 kilonewtons acting downward. We have RR and RL. Now, intuitively, I can guess that if this force is acting downwards, that this is going to try to want to pull down, not push up. So my guess is that this is wrong, but I always start assuming it's going upwards and see how my calculations go. We have 0.4 meters and 0.4 meters. Sum of the forces in X equals 0, Rx equals 0. Let's sum the moments about RL again. Again, you could pick whatever point you want. I just find it nice to be consistent and always pick RL. If you want to do something to practice, do these same 3 examples again, picking different key spots to spin it about, and go through it and see if you get the same answer. And you will see that it doesn't matter what point you pick, you will get the same answers, the same way we did on the Dave and Shannon one. So let's take a look at this. If it's passing through the point, there's no eccentricity, which means it doesn't cause it to spin. So RL times 0 is 0, and RX times 0 is 0. Put a thumbtack here and try to push my paper this way. It's going to spin like that, which is positive. So RR times my eccentricity is 0.4 meters. My 1.5 is acting this way. It's trying to spin my paper like that if I put a thumbtack there, or minus 1.5 times 0.8. And I want to know what it takes for this to be in equilibrium. So if we solve this, we get that RR equals 3.0 kilonewtons. Now, intuitively, if you shorten that backspan, I think you can infer that this needs to pull down with more force to hold it in place. Let's see if that actually is true. Let's sum our forces in our y direction now and see what it takes to be in equilibrium, or for the sum of all of those forces to be 0. We have RL acting upwards and our RR acting upwards, which we calculated was 3. It's a positive answer, so my arrow was right. It really is acting upwards. And we have our 1.5 kilonewtons acting downwards. We rearrange this and we get that RL equals minus 1.5 kilonewtons. That means I drew my arrow wrong. We have 1.5 kilonewtons applied load. We have 3.0 kilonewtons acting upward. And minus 1. No, we don't want the minus because I've redrawn my arrow here. We've got 1.5 kilonewtons. And let's keep our dimensions so that it's a true free body diagram. So the shorter that backspan, the more force we need to pull down with to keep this in place.